And let's get in to these slides, okay? So this is where we left off, right? We got that this is our um, wave function for the two-dimensional particle on a ring. Remember, two-dimensional because it's rotating in and out of the xy plane, where the angular momentum is pointing up on the z-axis, okay? And what happens when we look at the square modulus becomes independent of phi. And so what that means is the probability density is indefinite. We have a large degree of uncertainty in this, okay? And so what that means is angular momentum Jz and angle phi become a set of complementary observables. We're going to explore this, like I said, in much more detail in this talk and this lecture, as well as the next lecture, okay? So what we need to do, we need to come up with a new operator for angular momentum. And we're going to borrow more stuff from classical mechanics, okay? So the orbital angular momentum, so that can be described with classical mechanics, all right, given by Lz, which is x times py, momentum in y, minus y times px. So this is a classical mechanics equation. We also know from quantum mechanics, whoa, I don't know why my alarm just went off. It scared me though. Anyways, I'm keep going. I'm gonna keep recording. So the linear momentum operator, we know from quantum, is this, okay? So when we're gonna combine these two things, right? Because we have momentum here and we have x, and so when we combine these two things, we get this two-dimensional, I'll say two-dimensional Cartesian, I think you spell that with two S's. So this is our two-dimensional Cartesian coordinate scheme with x's and y's. However, if you recall, because in this case we only have constant radius and we're not dealing with the theta dimension, at least not yet, our orbital angular momentum operator just simplifies to h bar over I times dd phi. Okay, it becomes very simple. Don't confuse that with the kinetic energy operator for rotations, right? Let's just back up and look at that one hot second. The kinetic energy operator, remember, was negative h bar squared over 2I times d squared d phi squared, okay? Our angular momentum operator is going to be h bar over I times d phi, all right? And so what is the big deal about this thing? Well, for one, we need to check that this is going to be an acceptable operator, okay? And so I've already given you the results here. So when Lz operates on psi ml, right, where here's my psi ml, then our result is actually ml h bar times psi ml, okay, right? So we get the eigen value, which is ml h bar, and we return back the eigen function, psi ml. And so I'll just remind you really quick to do this operation of Lz on psi ml, right? So it's just simply h bar over I and the derivative in phi of this equation, psi ml, okay? And so when we do that result, we get back ml h bar times psi ml. So I'll write that, it's ml h bar, and then that becomes divided by 2 pi e to the I ml phi, right? So that e I ml phi divided by root 2 pi is psi of ml. So this is fantastic. So we're working in the right direction with this orbital angular momentum operator. We recognize it's a valid operator because it gives us an eigenvalue. So we're going to use this angular momentum operator to continue exploring this uncertainty principle given by angular momentum and angle. But before we continue with that, I want to expand this particle on a ring model